Okay, in this video we move on to multiple regression, multiple linear regression. In simple linear regression, we're able to plot one y variable for when we have one independent variable. But what if we have a whole bunch of independent variables? What we do not want to do is do a whole bunch of scatter plots, because those are treating these independent variables separately and not taking into account any other independent variables. So when you have multiple inputs, you don't want to just do a bunch of scatter plots, you want to do multiple regression. So let's do multiple regression with this data set. And if you've been in any of my classes, you've probably seen this before. What we have here is data from 1976, the NFL football season. So this is the Washington Redskins, Minnesota Vikings, New England Patriots, Oakland Raiders, Pittsburgh Steelers, on and on down. And this is the number of games they won in 1976. And then these are a bunch of things that we think influenced or affected games won. These are offensive stats. These are defensive stats. These are some special team stats, and this is a turnover and how well you cheat or how much you cheat. And I just want to know which of these influence these and to build a multiple regression model. So when we do this, what you do not want to do is go build a bunch of scatter plots. That doesn't work. What you want to do is to go under the data analysis and go to regression. Like that. And once you grab it, your Y range, and then your X range. And notice my X range are all contiguous. They're attached, they're adjacent to each other. You're not going to be able to grab data sets that are all over the place. So it needs to be structured data before you do this. It's the same number of rows. The very first row that I chose is a label, so I tell Excel that. And I'm going to go ahead and put the data right on this worksheet. It'll be busy, but I'm going to put it here. I'm going to put it starting right there. Right there. And I'm not going to get any of this additional information. This is all I need. So I'm going to run that. And there you go. Just like that, we've got this amazing, very quickly done multiple regression analysis. So I'm going to highlight some things for us that we're going to spend some time on. I'm going to highlight this. We're going to highlight these two. We're going to highlight all of these. And then finally, we're going to look at these. Those are the things I want to talk about. So the very first thing we have to do is evaluate, is this a good model or not? And the very first place you start is right here. This is where you start, first place. And so I'm going to insert a comment, and then if greater than 0.05, stop. Model is useless. Now I'm somewhat arbitrarily picking 0.05, but essentially what this tells me is a hypothesis test telling me, is my regression model, is any of it of value? So it's like a gatekeeper test. Is there anything of value in this? And when you have a p-value, and the assumption is that nothing is important. That's the assumption. So what this is a p-value, which is a probability that the null hypothesis is true. So what this is essentially a number that tells me the likelihood that nothing is important. And I'm going to show that as a number with decimals instead of it's showing it as a scientific notation, but I'm going to show it like that. And if that number's big, then you want to stop right then. There's no reason to look at anything else if that number's big. The definition of big is if it's bigger than 0.05. You might use 0.1. You might want to use 0.01, but don't use anything bigger than 0.1 for sure. So in this case, this number is much smaller than 0.05, so keep going. Otherwise, keep analyzing. So the question we're asking, is this a good model? That's your first step. Your second step is you look here. This is r squared, just like what we did before. R squared is the amount of variability accounted for in the model. So of all the reasons that we win the games, 78% of that is accounted for in these 8 variables. That's awesome. If you had to think from 0 to 100%, I've just got almost 80% of my variability accounted for in these eight variables. Obviously, there's other things that affect if we win or lose. You know, home field advantage, the weather. There's other things that affect, but for the most part, we pretty well have a pretty good model that predicts wins based on these 8 variables. That's what this is. So that's an incredibly high number. The next thing you look at is adjusted R-squared. Adjusted R-squared. And this tells you it's like R-squared, but it tells you, do you have an efficient model? Its upper bound is R-squared. So adjusted R-squared can never be bigger than R-squared. So the maximum that adjusted R-squared could be is 0.77. And it's not. If there's a difference, then inefficiencies exist. I can't spell inefficiencies, something like that. So what do I mean by inefficiency? That means that some of these variables don't add value. Some independent variables do not add value. And that means that we can have a better model, or as an effective a model, but get rid of some of these variables. And think of variables as it cost us time and effort to collect some of this data. And I want to have the smallest, the ideal is you have the smallest model possible that adds value. You don't want a model with a bunch of variables. You want the tightest with fewest number of variables that you can have to predict things. So I want to get rid of the things that aren't important. That would be better. Now, how do we know if there's a difference? Generally, what we look at is if there's a difference of 10%, we probably have variability. And it's a relative number. So the relative error, or the relative gap, relative difference, is equal to what we start with, what we start with minus this in the numerator divided by our denominator, and let's show that as a percent. So there you go. We have a 12% difference between these two, and our goal is to make that less than 10%. You might want to make it smaller, but that's how you want to set about in doing these. So that's I guess I should shade that. So we've looked at this. If that number was bigger than 0.05, stop. There's no reason to do anything else. The next thing is to look at this, make a decision on is it a good model or not. Then look at this one and say, is there any inefficiencies? And in this case, I would say we have inefficiencies. So now we look down here. We look down here, and I'm not going to put a rule because I think that's tough to do. But what I'm going to say is that smaller is more important. When you look at p-values, smaller p-values are more important. So if I had to look, I'm going to go ahead and just sort it. I'm going to take this data and sort it if I can. Sort by, I don't want to do that. I don't want to have headers. Sort it by column P from small to large. There you go. So that variable, this variable is the most important one. X2 is pass yards. Pass yards is the most important. If I had to go out and say, why do we win games in 1976, it's how many pass yards I could get. And then the least important thing is X3, which is punt yards. My punt yards. If I had a punter that could punt the ball a long ways, it doesn't help me win any games. This p-value is really big. This one is really small. So if I would just throw out the bottom 4, look where my break point on my p-value is. I'm essentially saying if I have a p-value bigger than 0.18, I'm throwing it out. How you decide which variables to throw out is completely up to you. There are rules we could code. Some people look at it as a 10% rule, so they would throw out anything less than that. Some people would do something higher. I don't, that changes from problem to problem. I will say that if you get a p-value bigger than probably 0.4, 0.2, 0.3, you probably ought to throw it out. So all of these variables are certainly not important. So I should focus and build a model just based on that rule, just based around these variables, x1, x2, x7, x8. So let's go do that. I'm going to go copy this entire worksheet, move or copy, create a copy, move it to the end. Here's my copy, and I've got all this other stuff, but I'm going to now get rid of the inner, the x4, 5, 3, and 6. I'm going to get rid of these columns. These are the ones that aren't important. Now I'm left with just these 4, and I'm going to redo my regression. So let me clear all this out, or just insert. Let me do that. Insert. And do the same thing. I'm going to do data analysis regression. My y variable is the same, but now my x variables are 4 of these 4. And I'm still going to put the output, in this case I'm going to put it right there. Hit OK. Oh, I've got overlapping. So I lost some stuff. Sorry, but so that's the problem with doing this. It overlapped. That's all right. I didn't mean to do that, but that's all right. I'm going to hide some of this stuff anyway. Like that. So let's look at some things. This is the new I'm not going to delete just yet. This is the new p-value, so it's still small, so this is good. This is the new r squared. This is the new adjusted r squared. Here are my new p-values. And here are my new slopes. Now I'm going to get rid of some of this stuff because I want to show them head to head. So here is the new model. Here's the old model. Look what happened. When you get rid of variables, your r squared will always go down. I lost the amount of variability accounted for. I lost almost 2%. It went from 77.8 to 76.2. So 1.6% of my variability is lost. That's always going to happen when you reduce variables. You're never going to get a higher r squared when you get rid of variables. That's just facts. However, look at the efficiency of the model. It went up much more than this went down. I went from an adjusted r squared of 68 to an adjusted r squared of 72. So if I calculate this for this problem, now my relative difference is 5%. So this is a much better model. I lose a little bit of total variability accounted for, but my efficiency is much better, and I've got a model that only has 4 variables in it. Only 4 variables. Now I'm going to redo this again, and I'm going to generate it in a new worksheet so we can do some final analysis. I'm going to do the same thing I just did, do regression. And this time I'm going to put it in a new worksheet so it's neater. Okay, there's my output. We've already talked about these. We've talked about these. Now let's build us a model. So my wins is equal to 4.16 plus 0.003 multiplied by x1, which is rush yards, plus 0.0037, just a little bit more, times pass yards, minus 0.003 times opponent rush yards, minus 0.002 times opponent pass yards. So that's my regression equation. If I'm trying to figure out how many games I'm going to win, if I can estimate these 4, I can come up with the game of wins. And that's the equation, just pulling these coefficients. So I'm going to go over here and put in an if statement, if, and I'm going to say, if my rush yard, let's say I've got a running back that's going to run for 2,000, or I'm going to have a running back that runs for 2,000 yards, and I got a quarterback who throws for 1,700, and a defense that gives up 1,600 yards on the ground and maybe 1,800 yards in the air. How many games am I going to win? Then, so look at the little trick I'm going to do. I'm going to put a 1 up there, and then I'm just going to do a sum product of these 5 against these 5. My wins would be equal sum product these estimate, these coefficients against these inputs. And the reason I put a 1 up there, because that's just the intercept, I just add it. So it's that 4 times 1 is just 4. And there you go. That's how many games I expect to win based on this model. I'm going to win 8 games or 7.6 games. If I can go out and find a quarterback and I can throw for 2,200 yards, wow, I'm in the playoffs. If I can get my defense maybe to stop the pass a little bit better, maybe drop this down to 1,600, that didn't help too much. But maybe if I go and do the same thing on defense and get a defensive tackle like Mean Joe Green for the Steelers and drop this down to 1,400 yards, which is now I've got a chance to win the Super Bowl. So these allow me to go make decisions against this to see how I'm going to predict how many games I'm going to win. So looking back, what we did, we have multiple variables, so we do multiple regression. From that, we walk through these. Once we have a model that we like, we finally use it to do some prediction and use the model. Thanks.